Hello everyone, welcome back to my channel Shraddha's Physics. This video is based on statistical mechanics for the core 14. So today we will see the Wien's distribution law. Let us consider that the radiation, here the radiation lies between the wavelength region lambda and lambda plus d lambda, and it is isolated in the enclosure. Let this alone be subjected to the adiabatic expansion. So as in case of Wien's displacement law, as we have discussed in the adiabatic expansion, similarly in case of Wien's distribution law, here we are also considering that in case of adiabatic expansion, here the radiation it lies between lambda and lambda plus d lambda. Let this u lambda d lambda be the energy density of this radiation, so that we can write the energy will be equal to this energy density, that is u lambda d lambda into the volume B. When these radiations alone are expanded adiabatically, then the work done in this adiabatic expansion we can write delta W equal to P into delta V. Here we are considering that the diffuse radiation. Diffuse radiation means the radiation it can be possible in every directions. So in case of the normal incidence, we know the pressure equal to the energy density U, and in case of this diffuse radiation, this pressure equal to 1/3 of the energy density. Here in the wavelength region, that is lambda to lambda plus d lambda, our energy density is u lambda into d lambda. So here in the case of pressure, that will be u lambda d lambda divided by 3. So simply just substituting, we will get 1/3 of u lambda d lambda into this is your delta V. Again from the first law of thermodynamics, we can apply delta U plus delta W equal to dq or delta Q. In place of U, we can write this is u lambda d lambda into V. So here in place of U, we are writing u lambda d lambda into V plus delta W is 1/3 of u lambda d lambda into delta V, which is equal to delta Q. Here we are considering that the system is in adiabatic expansion. Since in case of adiabatic expansion, we know the heat of the system remains constant. Since the heat remains constant, so the delta Q change in heat will be 0. Hence delta Q will be equal to 0 in case of adiabatic expansion. Now differentiating this, these are 3 terms. So first delta U lambda into d lambda into V plus u lambda delta d lambda into V plus for the third term u lambda d lambda into delta V plus this term 1/3 of u lambda d lambda into delta V, that is equal to 0. Now again you can see this is u lambda d lambda delta V, here also u lambda d lambda delta V. So taking this term common, this will be 1 plus 1/3, that will be 4/3 of u lambda d lambda into delta V, and this 2 term remains as it is, that will be equal to 0. Now dividing throughout by u lambda d lambda into V, so this term will be d lambda B get cancelled. So d lambda B cancelled, so the remaining will be delta u lambda by u lambda plus again in this term u lambda and V it get cancelled, so the remaining term will be delta d lambda divided by d lambda. Again dividing with this 4/3 u lambda get cancelled, d lambda get cancelled, and the remaining term will be 4/3 of delta V by V, that is equal to 0. Clear? Since we know this d lambda changes in the same way as lambda, so we can write delta d lambda by d lambda will be equal to del lambda by lambda. So in this place, if we will replace this term as delta lambda by lambda, so this equation will becomes del u lambda by u lambda plus delta lambda by lambda plus 4/3 of delta V by V, that is equal to 0. Again we know from the Wien's displacement law, that is 1/3 of del V by V equal to del lambda by lambda. So in place of 1/3 of del V by V, we can put this is your 4 into del lambda by lambda, and every other term remains as it is. So here this is del u lambda by u lambda plus del lambda by lambda plus this term as your 4 delta lambda by lambda, that is equal to 0. If I will sum these two, that will be 5 del lambda by lambda. Again taking this to the right hand side, this will be del u lambda by u lambda equal to minus 5 del lambda by lambda. So integrating this equation, this will becomes log of u lambda, and this will be equal to, this is on the left hand side, this will be log of u lambda, that is equal to minus 5 log of lambda. Or we can write this is your plus 5 log lambda equal to 0. We can write like this, taking this term as plus 5 del lambda by lambda equal to 0, we can write like this. Now this will be log lambda power 5, we can write like this 5 as your log lambda power 5, again log a plus log b, that will be log u lambda into lambda power 5, that is equal to some constant. Now this u lambda into lambda power 5 will be equal to u lambda prime into lambda prime power 5. Here this u lambda prime is the energy density or the density of radiation when the wavelength is lambda prime. So comparing this, we can write also u lambda divided by u lambda prime equal to lambda prime 5 power 5 divided by lambda power 5. Again we know the lambda t equal to constant, we know lambda t equal to some constant. So that is the wavelength is inversely proportional to the absolute temperature. So in place of lambda power 5, we can write this as your 1 by t power 5, and in place of lambda power 5, we can write 1 by t power 5. So this is the reciprocal of this. Hence u lambda into lambda power 5 will be equal to, this will be a prime some function of lambda and t, we can write like this. Again if we will multiply d lambda on the left hand side and right hand side, so this will be u lambda into d lambda equal to this lambda power 5 here, a prime by lambda power 5, the function of lambda t into d lambda. The emissive power E lambda, it is proportional to the energy density u lambda. So in place of u lambda d lambda, we can write E lambda d lambda, since E lambda d lambda is proportional u lambda d lambda, so we can write E lambda d lambda equal to a by lambda power 5 function of lambda t into d lambda. This is known as Wien's distribution law. Here this E lambda d lambda, it denotes the amount of energy it contains in the spectral region from the wavelength lambda to lambda plus d lambda, it emitted by a black body at the temperature T. So here you can write E lambda d lambda will be equal to a, this will be t power 5 divided by lambda power 5 into t power 5. Here we have just multiplied and divided t power 5 into this is your f of lambda t into d lambda. So now we can write this as a t power 5 into, this will be lambda t power minus 5 f of lambda t d lambda. Here you can see that this term contains lambda t. So this is, again we can write this total term as a function of capital F of lambda t. So in this place we are writing capital F of lambda t. So this will be E lambda d lambda equal to a t power 5 f of lambda t into d lambda. So here from this relation you can write, this is a, this a is your constant and this is your f of lambda t and this is your d lambda. So you can write from this E lambda divided by t power 5, that will be equal to E lambda prime divided by t prime power 5. So this we can say that in this energy density, when the absolute temperature is T, at this time the energy density will be E lambda, where lambda is the wavelength at this particular temperature T, and similarly at the wavelength lambda prime, if the absolute temperature is T prime, then the energy density will be E lambda prime. So here what we concluded that lambda t equal to lambda prime into T prime, and E lambda by t power 5 will be equal to E lambda prime divided by t prime power 5. So here from this graph what we concluded that the energy is not distributed equally among all the wavelength. It means that as the wavelength increases, you can see that this is fast wavelength, this 1, 2, 3, 4 like this. If we will consider this fast curve, okay, for this fast curve you can see that when the wavelength increases in this fast curve, so the energy density will, the energy will increases up to this much, that is lambda m, and after that with the increase in this wavelength the energy will become decreases. It means that initially it will increases up to a maximum value and that after it will decrease. It means that the energy value will decreases with the increase in the wavelength. In this curve you can see we are considering this is the temperature T1, T2, T3 and T4. The T4 temperature is very less as compared to the T1. So, in this case, in this T4 temperature region we can see that the maximum wavelength region, this is the maximum value of the wavelength and this is the maximum value of the energy. And in case of the T1 temperature, here this is the wavelength region, that is the maximum wavelength is at here and this is the maximum energy value. So, in between these two you can compare that when the temperature increases, this will be T4 is greater than T1. When the temperature increases, when the temperature has the maximum value, then it has the shorter wavelength. Otherwise we can say that when the temperature has the higher value, then at that, when the temperature has high value, at that case the wavelength is small, or we can say that when the wavelength has the larger value, at that case the temperature is low. And also we can say that when the temperature is low, the energy density is low, and when the temperature is high, at that case the energy will be maximum. Hence we can say that with the increase in the temperature the wavelength decreases, so that hot object has the shorter wavelength and we can see the blue visible light, or for the cold object, that is for the longer wavelength region, we can see the red visible light. So, this is the conclusion for Wien's law, that is Wien's displacement law as well as Wien's distribution law. So, this is all for today. Thank you.